Okay, let's do this as straightforward as possible. We're talking about quadratic functions, and this essentially is a function that has as its base, as its parent function, y equals x squared. You might have a coefficient in front of that that's different than 1. You might have a b term, you might have a constant term. So it would ultimately look in this form, okay? But that's it. It's going to be an x squared term. And so what? Well, those will always, when graphed, form a parabola. And what is a parabola? Parabola is just what you see down here in this graphed illustration. It is a curve like this. It is nonlinear, okay? And it models certain situations where the rate of change is not constant. There's a lot of things in nature that follow this, like the speed, trajectory, and of falling or thrown items, or other things like that, okay? The graph of quadratic function is symmetric, and that means that you can draw a line right down the center of it through its vertex, which is that highest or lowest point right here, and everything, every point to the right of it will be the exact same distance as a point just to the left of it, like that, okay? So if you know a point here is 1 unit away that way, you know it's 1 unit away on this direction as well, okay? Got a highest or lowest point corresponding to a maximum or minimum value. If it is the highest point, that's the maximum. And if it's the lowest point, as you see in this illustration here, the lowest point is down here at that origin, okay? That'll be a minimum. So we have this parent function of y equals x squared, and it's a parabola, and there's an axis of symmetry running down the center of it. That's the big ideas for this page. Let's keep going. Now, we call the highest or lowest point the vertex, okay? It sits on the axis of symmetry, and that's going to be helpful once we know what the axis of symmetry is. It'll allow us to plug that x value into the equation to find the actual y value and therefore the coordinates of the vertex exactly, okay? But if the coefficient is positive, a is greater than 0, meaning it's positive. If the coefficient of the x squared term is positive, it's going to open upward like that, and therefore there'll be some lowest point. There'll be a minimum point. Okay, the vertex will be the minimum. Now, if you have an a value that's less than 1, negative coefficient on x squared, then it's going to open downward. It's going to look like this, and you will get a highest or maximum point on that parabola, okay? That's a big idea. So let's take a look at what we might need to do with it. Now, what are the coordinates of the vertex of each graph? We're going to about to see a couple of graphs. And what is the maximum or minimum? Can you have both a maximum and a minimum? The answer for parabolas is no. You will never have a maximum and a minimum. It's either going to open upward, in which case there's the lowest point, but not any highest point. It'll keep going for forever, or it will open down and you will have a highest point, but you will not have a lowest point. It will keep on dropping forever, okay? So let's see what the graphs that they have for us are, okay? What are the coordinates of the vertex? Well, this is just reading it right off of the page, and you can see that it's 0, 3 is that highest point right there. And since it's the highest point, it's a maximum. What about this vertex of this parabola? It is that lowest point right there. It's a minimum. And what are the coordinates? 1, -1. Pretty basic. You try it. See if you can identify whether it's a minimum or a maximum for the vertex point and what are its coordinates. So since we know that a parabola is symmetric, it makes it a little easier to graph, because what we can do is we can find where the vertex is, and then we can find several points on one side and reflect that set of points across the axis of symmetry, and we'll have a matching number of points on the other side, So for graphs of the form of this, y equals ax squared, where the only thing you've done is change the parent function to have a different coefficient, okay, then it's always going to be the origin. Essentially what the origin says is if you plug in 0 here, what's 0 squared? 0 times 0 is 0, and 0 times a, anything times 0 is 0, so whatever a is, it's going to be 0. So if you plug in 0 for x, you get 0 for y. That's going to be the vertex, okay? So the axis of symmetry is a vertical line, which means it's cutting through the x-axis, right? Remember what, if we say, what is this line as an equation? Well, if it cuts through x equals, let's say 3 there, okay? It's a vertical line cutting through the x-axis at 3, and therefore the entire equation for that line is x equals 3. Everywhere on that line, x equals 3. Okay, so let me clear this out. Oops. Now, if we're going to graph this, how do we do it? Well, we will make a table. We'll make a table of values that we're going to plug into here and find out what comes out, and then we'll have sets of coordinates that we can graph. Okay, and so it says make a table of values so that we can graph it. And then what is the domain and the range? What are all of the possible values you can plug in, and what are all of the possible values that would come out? Okay, and it would be like you draw it as an inequality. It's got to be greater than this, or less than this, or greater than or equal to, less than or equal to. This particular note says, what are good values to choose for x? Well, we can see that we're going to be taking a third of this x squared term, okay? So since that's true, if we use multiples of 3, or we get x squared terms that are divisible by 3, then taking a third of it will always leave us with integer values. So since we can pick which particular numbers we're calculating, remember, all of the numbers will eventually be somewhere on the graph, right? All of the x values that we're allowed to use. But we're going to pick ones that give us key points where we're going to make graphing easier by. Okay, so what do we do here? Well, they pick 0, 3, and 6, so that when you square it, you get 3 squared is 9, 1/3 of 9 is 3. We get an output value of 3. If we put in 6, 6 squared is 36, and 1/3 of 36 is 12. So for an input of 6, we get an output of 12. These are coordinates. Here we go, 0, 0, 3, 3. You notice that they're going by 3 units for each box in both directions. So 3, 3, 6, 12. And as we know, there's a line of symmetry here. So if we go 1 unit to the right for that point, we can go 1 unit to the left of the axis of symmetry and find another point. Same thing here. If we go 2 boxes, really 6 units to the right to plot that point, we can go 6 units to the left to plot that point. Now we have a symmetrical set of points that we can sketch with a curve. Okay. The domain is all real numbers. In these theoretical problems, or I should say not ones that are applying to real life situations, unless you see a real life situation that limits what you can put in, no reason why we can't plug any x value in here from negative infinity all the way to infinity. So all real numbers will work for our input. But what's going to come out? Well, we're never going to get a value that's less than 0. That minimum point is 0. Since we're never going to go below 0, the y value that comes out will always be greater than or equal to 0. Yep. Okay, so the output value for these will either have, they will have a limit on y that's either a lowest point or a highest point. Okay, so let's take a look at what you can do. Here, you're going to graph this, and what are the domain and range values? Okay, oops. Yep, so give that a go and compare your answer to mine when we restart it. Now, what we see here is that it's saying that the coefficients of this quadratic function, the a squared term, the a value of that coefficient of the squared term will be what determines how wide or narrow it's graphed. Wide would be like this. Let's say we've got the parent function, y equals x squared, looking like this, okay? So if you go over this many units, you go up that many units, let's say. Okay, well, if you have a number in front of x squared that's greater than 1, let's say 3, well, now you're going to go up 3 times as high. That's going to be the case. So what would that do to the curve? It would make it steeper, and it would appear more narrow because each point is going higher than it would be if it was just a 1 there. Okay, so for values greater than 1, it's going to stretch the parent function vertically up and essentially narrow it. Those points will be closer in than the red parent function is. Okay, so what happens then if you have an coefficient on x squared that's less than 1? Let's say it's 1/10. Okay, well, if the parent function looks like this, then you say, okay, well, if I, for every point that I go over, I normally go up that much. Now, if I go over, I'm only going to go up 1/10 as much. And this curve is going to widen out a lot. Okay, in fact, the closer it is to 0, the flatter it's going to be, the wider it's going to be, versus if that number is greater than 1, remember, it's going to make it narrower and taller, stretching it vertically. Okay. What about negative? What about if we have a coefficient that is negative? Well, the fact is, in terms of how it stretches or changes the shape of it, if we went from having y equals x squared here to y equals negative x squared, the only thing that that's doing is saying, instead of going over and then up, you go over and then down, but you go down the same amount. So that would be the exact same shape, just flipped over the x-axis. Okay, so the negative won't affect how wide or narrow it is. That'll just affect whether it's opening upward or downward. Hopefully that all makes sense. Okay, so if we take a look at this, what is the order from widest to narrowest? They want the widest to come first. We're going to say, okay, well, what's the biggest coefficient? Forgetting about the negative, we're taking the absolute value. And -4 has the greatest coefficient. Okay, this has the smallest coefficient absolute value. This is of 1. So for the widest, remember the widest is going to have that lowest number, okay, closest to 0. That's going to flatten it out and widen it up. Instead of going up and this far, you're going up and not as far up for smaller numbers than 1. Okay, so the widest one will be this right here, the widest. Okay, what about the narrowest? Well, the narrowest is going to be the one that's stretched the most, up or down, and that's going to come from big numbers. Okay, so this is going to be the narrowest right here. And of course, this one in green will land right in the middle of that 3. Now, as I said, it says, does the sign of it affect the parabola's width? Nope, that will just flip it, open it upward or downward, and that won't, the width of it won't be affected by that. Okay. Now, of the 3 graphs, the widest is 1/4, y equals 1/4 x squared. Make that association. The smaller numbers will mean you go up less, and therefore it'll be wider and flatter. Okay, and the greater number, absolute value, negative or positive, if it's a higher absolute value number like 4 is, it's going to greatly stretch it 4 times as far as it would be for the parent function. Okay, and it will end up being the narrowest. So widest to narrowest is 1/4 x squared, then x squared, then -4x squared. Try this, got a problem, order these, see how you do. Okay, one last big idea here is that a c value, a constant value at the end, will either just shift the entire parabola up or down. And we're going to kind of explore why that is. Okay, let's take a look at this. Y equals ax squared plus c. Okay, where we have a constant value. How does the graph of this, y equals 2x squared plus 3, differ from just y equals 2x squared? Okay, it's shifted somehow. How is it shifted? Well, if we're going to make a table of values, and we should, what values should we choose? Well, if we, for both functions, if we choose the same values, we'll be able to see what's going on at those particular points. So we choose the same values. We say, okay, let's plug in -2 to that one and then -2 to that one. And what you will see if you compare these is that this +3 makes each output value 3 higher every time. And so if you go over here and you're normally going up there, you'll now be 3 units higher. If we're going over here normally and going up there, we'll now be 3 units higher. If you're here at the origin, you're going to be 3 units higher. The whole thing is shifted up. Because it's positive, it's shifted up 3 units. Correct answer is A. Okay. What about these two? How are they related? Give us your best answer. When we restart, you'll see how you did. Okay, first let me say that if you were in the 2020-2021 school year, you can skip this. We're not going to cover it this year and not doing it in this lesson. You won't see it on the tests. But I'm putting it here just for the sake of kids that are seeing this in a different year or for teachers that want this explanation. So feel free to skip over to the very end to the lesson check problems. But here you go. We can use quadratic functions to model the height above the ground of something that's dropped from that height, C, okay? Let's say C is 20, that means you're 20 feet above the ground, and this is gonna model the time, T is the time in seconds, and this is gonna model what happens to the height. You can see it's a negative because it's gonna be falling, and it will get faster as the seconds go on because as you drop something, it starts out slow and speeds up. So, height above the ground after T seconds, if it started with an initial height of C, okay? So an acorn drops from a tree branch 20 feet above the ground, so that's the +20 that's there. This -16t squared is standard for anything that gets dropped, okay? That's just gravity at work, okay? That gives the height of the acorn in feet after T seconds. What's the graph of it and at about what times the acorn hit the ground? So what do we know? Well, we know it's 20 feet above the ground, okay, and the function is based on is going to be the acorn's height. The graph, we need to make the graph, and we need the time that it hits the ground, and so we'll use a table of values. The question they're asking, can you choose negative values? No, before the nut drops from that branch, this whole equation does not apply. So you can't use negative time here. Okay, T won't be negative. But what do? Well, we say, okay, what if it at 0 seconds from the time that it fell, it's right there, just being released at that 20 feet. After half a second, it's there. After 1 second, it's there. After 1.5 seconds, it's not really there. It doesn't go embedded 16 feet into the ground. What that just indicates is that somewhere between 1 and 1.5 seconds, it reached 0, which is the height, which is the ground. Yep. Okay. If you were to graph it, it would say you can graph the first 3 ordered pairs. You can't plot 1.5 comma -16. Height cannot be negative. It's not going to be below ground. So the acorn hits the ground when the height is 0. Okay. And from the graph, you can see that that happens at just after 1 second. Okay, just after 1. Yep. Hopefully that makes sense. Now, your got it problem is what happens if it was dropped from 70 feet above the ground. So this is +70. It's going to give you a different set of values here that you're going to want to calculate out. So what's the graph? Make that table to know, and about what time does the acorn hit the ground? And you can look at, again, it's going to be where it's 0. So here, remember, it's moving faster and faster and faster. So if it's only 4 feet above the ground here and it's moving fairly fast, it's not going to be much after that it hits the ground. So keep that in mind when you make your table. And then what are a reasonable domain and range for the original function? What's a reasonable domain and range for it? See if you can answer these questions, and then you'll restart it when you have them. Okay, this lesson in this unit's fun because we're now starting to graph nonlinear things, which is different from what we did earlier in the year. But hopefully this makes sense to you. So you can sign up for office hours, ask me questions however you want to do it, bring questions to the start of class if you've got them, and do these lesson check problems and see if it all makes sense to you. You can restart to compare your answers once you have them. Okay, good luck with this.